The science behind speed, mastering algorithmic efficiency through rigorous analysis in the fast-paced world of software development. The difference between a snappy application and a sluggish mess often hinges on one fundamental factor: the quality of algorithm implementation. This is where algorithm analysis becomes indispensable, offering developers a structured approach to evaluate code performance before deploying it to production environments. Understanding algorithm behavior isn't merely about counting lines of code. It involves dissecting computational complexity, measuring resource consumption patterns, and identifying potential bottlenecks through mathematical modeling. These skills form the bedrock of efficient software engineering practice. Fundamental concepts in algorithm analysis. At its core, algorithm analysis revolves around quantifying two primary factors: execution time and memory usage. By establishing precise measurements for these parameters, developers gain insight into an algorithm's scalability and overall efficiency. Execution time analysis focuses on determining how runtime increases with input size. This leads us to the most widely used framework, Big O notation, which categorizes algorithms based on their growth rate rather than exact execution times. Asymptotic notation expresses upper bounds, O, lower bounds, omega, and tight bounds, theta, for algorithm performance characteristics. Time complexity evaluates how processing time grows relative to input size and space complexity. Measures auxiliary memory requirements beyond input storage. These foundational concepts provide a universal language for comparing algorithms. While concrete numbers vary depending on hardware specifics, asymptotic analysis reveals inherent efficiency traits independent of particular implementations. A classic illustration is the comparison between linear search, O, n, and binary search, O, log n. Though both find a value in a sorted array, their differing rates of growth demonstrate why binary search dominates for large datasets. Beyond Big O, advanced analytical techniques. While Big O gives a high-level overview, deeper analysis requires additional considerations. Amortized analysis, for instance, evaluates average case performance when operations occasionally trigger expensive computations. Take the case of dynamic arrays. Insertions usually take constant time, but when capacity is reached, the entire structure must resize, an O-N operation. Amortized analysis shows that over many insertions, the cost averages out to O(1). Recurrence relations offer another powerful tool for analyzing recursive algorithms. By expressing T, n equals A asterisk T, n/b, plus F, n, we can solve for closed-form expressions that define performance characteristics. This method was pivotal in evaluating merge sorts efficiency, leading to its proven O(n log n) worst-case performance. Understanding recurrence relationships enables precise predictions about algorithm behavior across varying input sizes. Case study: sorting algorithm. Sorting serves as an excellent domain for demonstrating analytical methods. Bubble sort, despite being intuitive, performs poorly with O(n superscript 2) complexity, making it unsuitable for large datasets. Quick sort introduces probabilistic elements, achieving expected O(n log n) performance, though worst case remains O(n superscript 2). This variability necessitates rigorous statistical analysis to understand typical versus extreme behaviors. Merge sort guarantees stable O(n log n) performance regardless of input order, but requires additional memory. Its space complexity of O(n) contrasts sharply with quick sort's O log n due to recursion stacks. This comparative analysis highlights how different approaches balance trade-offs between time and space resources. Choosing between alternatives depends heavily on specific application constraints. Tools of the trade: empirical evaluation methods. Theoretical analysis provides a foundation, but empirical validation through profiling tools adds crucial practical context. Modern IDEs integrate sophisticated performance analyzers that track function call frequencies and resource utilization during program execution. Profiling instruments like Prof and Valgrind enable granular examination of CPU cycles consumed by individual functions. Their visualizations help identify hotspots, Sections consuming disproportionate processing power. Benchmarking frameworks such as Google Benchmark allow systematic testing across varying input sizes. This quantitative approach complements theoretical estimates by revealing real-world performance characteristics. CPU timing measures differ significantly between architectures, making absolute runtimes less meaningful than relative comparisons. However, micro-benchmarking techniques account for these variations through careful test setup. Determining computational complexity. Analyzing algorithm complexity involves identifying dominant operations and establishing how frequently they execute. For iterative algorithms, this typically means examining loop structures and their nesting levels. Nested loops present special challenges, multiplying iteration counts. A simple double loop results in quadratic complexity, while triple nesting produces cubic time complexity. Conditionals require special attention. Short-circuit evaluation may reduce actual iterations, yet worst-case complexity assumes the condition never terminates early. Maintaining consistency in analysis ensures accurate upper bound estimates. Recursion adds another layer of complexity. Tracing the call tree helps determine base cases and branching factors, enabling derivation of precise asymptotic bounds through recurrence equations. Space-time trade-offs in design. Elegant algorithms often strike a balance between temporal and spatial efficiency. Hash tables exemplify this principle by trading increased memory usage for dramatically faster lookup times, average case O(1) versus O(n) sequential search. Pagination strategies represent another space-time compromise. Loading data incrementally reduces memory overhead while maintaining acceptable responsiveness, especially for large-scale systems handling streaming inputs. Data compression algorithms leverage this relationship too, employing complex encoding schemes to minimize storage footprint at the expense of greater decoding computation costs. Choosing the optimal strategy requires deep understanding of system constraints. Cloud-native applications might prioritize low memory footprints, whereas batch processing jobs could benefit more from maximizing throughput. Practical example: graph search algorithms. Graph traversal offers rich opportunities for exploring space-time trade-offs. Breadth-first search, BFS, uses queues requiring OV, extra space for node tracking, whereas DFS utilizes call stack space proportional to the recursion depth. Bidirectional BFS represents an innovative solution, splitting searches from both source and destination to reduce queue sizes by up to half. This approach maintains linear space complexity while improving time efficiency significantly. Advanced techniques like a asterisk search incorporate heuristics to optimize pathfinding, sometimes reducing exploration efforts substantially. However, storing heuristic information consumes additional memory compared to basic Dijkstra's algorithm. Each technique reflects different design philosophies balancing computational demands against memory restrictions, a recurring theme in algorithm optimization discussions. Empirical validation through profiling. No matter how thorough our mathematical models appear, nothing replaces direct observation of actual performance. Profiling tools give visibility into how an algorithm behaves when executed in real environments. Memory profilers trace allocations made by an executing program, highlighting objects contributing disproportionately to garbage collection frequency. Such insights help refine object lifetime management strategies. Timing benchmarks should always compare against relevant baselines. A well-designed experiment isolates variables of interest by controlling external influences like caching effects and disk I/O latency. Repeated measurement sessions capture performance fluctuations, allowing identification of consistent patterns rather than transient anomalies that might result from random environmental factors. Emerging trends in algorithmic research. Modern computing paradigms continue reshaping algorithm design priorities. Parallelism and distributed computing challenge traditional notions of sequential execution and complexity metrics. GPU acceleration leverages massive parallel thread capabilities, fundamentally changing performance characteristics for suitable workloads. Algorithms benefiting most include matrix multiplications and image processing tasks. Quantum algorithms promise revolutionary speedups for specialized problems like integer factoring and database search, though current quantum computers remain limited in scale and error correction capabilities. Machine learning is even beginning to influence algorithm selection processes itself, with automatic tuning systems optimizing hyperparameters in real time based on observed performance trends. The human element, applying theory practically despite sophisticated analytical frameworks available, successful application relies equally on human intuition and experience. Recognizing common patterns accelerates the analysis process considerably. Experienced developers develop an instinctive sense of algorithm efficiency. This code smell detection ability comes from repeated exposure to various patterns and their corresponding performance profiles. Code reviews serve dual purposes. Not only do they catch logical errors, but they also provide fresh perspectives on possible optimizations missed during initial implementation phases. Maintaining documentation about chosen algorithms and their rationale proves invaluable for future maintenance. This includes noting trade-offs considered during design decisions. Common pitfalls and how to avoid them. Newcomers often confuse big O notation with actual runtime performance. An O(n) algorithm might still lag behind an optimized O(n) log n implementation due to higher constants involved. Overlooking constant factors is particularly dangerous in embedded systems where microseconds matter critically. Optimizing inner loops and minimizing function calls yields tangible benefits here. Assuming uniform distribution of data types leads to flawed analyses. Median of medians algorithms perform differently based on input distributions than assumed in standard probability models. Lack of profiling after implementing fixes prevents verification of actual improvements. Always validate modifications with benchmark tests before declaring success in optimization efforts. Conclusion: through meticulous study of algorithm properties, practitioners gain the ability to engineer highly efficient solutions while meeting project requirements. Combining theoretical foundations with empirical validation forms the complete picture of modern algorithm analysis. To maximize impact, continually refine your analytical toolkit. Stay curious about new developments, question assumptions regularly, and apply knowledge creatively when tackling novel algorithmic challenges.